Okay, so let me also share my screen. Okay, last session I started our topic on normalization, and so we first of all we have to know what normalization mean in general, right? So in simple words, normalization is just breaking down your like big messy table into a few smaller tables that are related to each other without, preferably without like any dependency, because we want to minimize redundancy and ensure data integrity. More about like this with I can better explain this with examples. But in general, it's just breaking down your large messy table into smaller related tables. Now we have three normal forms, 1NF, 2NF, 3NF, and so the goal is to reduce complex user views and eliminate errors and inconsistencies. In general, if you recall the examples I provided last session about different anomalies, so if you don't normalize your tables and you just put all the information in one large table, then there there will be several anomalies when you want to, for example, insert your data, when you want to update your data, or when you want to delete some information. And for example, let's say here are just a few examples. Um, let's say you want to insert a new course like ECS 4412. Now in this table, as you can see, we have information about student, course, instructor. And now if you want to enter, for example, this new course, if no student has entered in this course yet, you cannot add the course or instructor information, right? So this is, for example, information about insertion anomaly. Then we had example about, for example, delete anomaly. That is, for example, if you delete a course, let's say ECS 3421, now you also lose the information about the instructor, right? Because Mona is only teaching the database course, and if you are removing database, you also lose my information. And next, we also provided example of update anomalies, like for example, if you want to update Dr. Brown's office or any other information, sometimes you need to update that information in several rows. Now, this table is very small, just for example purpose, but in reality, like in real world cases, you have mm, tables, for example, with more number of rows, let's say thousands of rows or millions of rows, and then it is not efficient to instead of updating, for example, one specific value, doing it in, for example, thousands of rows. It doesn't make sense. And also, if you forget to, for example, if in case of like manual update, if you forget to update one row, then your database also become inconsistent. So how normalization prevent anomalies? So we talked about breaking down a large table into a smaller table. So we know that we want to end up with if like more smaller tables, right? Now, how can we do this? We often have to have to find some functional dependencies that exist in our table, original large table, and get rid of those dependencies. I'm going to talk about these dependencies uh, today, which are very important, because if you can identify the dependencies, then you can better normalize. First, you can identify what normal form your table is. Second, you can better normalize your tables. Now, uh, here you can see, for example, sorry, I accidentally hit this. So as you can see, normalization here, I don't want you to know at this point how I normalize this table into like these two. In fact, there should be three tables. One table storing course information, one table storing instructor information, one table storing course information. So course, instructor, and student, this information about these three entities should be stored in three separate tables. Why? Like um, ideally we want to store information about each entity in a different table, and that's why when I was talking about ER modeling, I mentioned that when you convert your ER model to relational schema, each entity will become a separate table. Now, one reason is, for example, what I mentioned. If for example, you apply any changes to any information in that large messy table, then you have to apply that change in maybe thousands of rows. Now, we try to store information about each entity in a separate table. So as you see, we have information about course here in one table, information about instructor in another table, and we should have also another table here. I didn't have enough space to put this here, but in practice, you should also have another table for storing student information. And of course, like these tables should be related to a foreign key, right? Because in ER model, we can easily show the connection between our entities using those lines, right? So we connect them through line. But in your database, like actual database with tables, how do you want to show the link between the tables? Using foreign keys. Now, I'm just trying to review these in case you missed previous session and also to refresh your memory about this topic. So here we also saw several examples about, for example, update anomaly, deletion anomaly, and insertion anomaly. So this one in this red box, this is an example of update anomaly. So for example, if Matthew changes the advisor, then you must update both advisor last name and advisor email. And if you forget to update one row, your data become inconsistent. And deletion, we also had deletion anomaly. So let's say this blue one, this is an example of deletion anomaly. So if we delete a student, like for example, Marino, then you lose these advisor and department information. So you may not want to lose advisor information, right? You only want to delete the student. And we also had an example of insertion anomaly. So as you can see, if we cannot add a new department, for example, department biology, unless there is, for example, a student and advisor assigned, right? Because we don't have other information. And this is exactly why we do normalization. So let me also, this is also about the insertion anomaly that I just explained. So this is why we normalize. We want to separate, for example, students, advisors, departments, and different entities into their own tables so that we avoid like these headaches. This is also an example of normalized relations. So one table is department, like storing department information in department table, advisor information in advisor table, student information in student table. Now, if you see in each table, for example, in the advisor table, we also have one department information, like department name. In practice, it's better to put like department ID because department name may not be a good primary key. But like this was just for the sake of example, we assume that these are unique, and department name here in the department table is your primary key. So when you connect department to advisor table, or these entities in your ER model were connected, right? Because, for example, each advisor should work in the department, right? And each department has several advisors working in that department. So there is a one-to-many relationship between advisor and department, and obviously there is a link between them. Now, where should you add the foreign key? Advisor, of course. Yeah, that's why you can see the department in the advisor table. You always add it to the many side. Exactly. So because in this case, you don't have any issue. Each advisor here, right? Each advisor works only in one department. So we don't have an issue with like storing multiple values in one cell. But if you want to add, for example, advisor name or advisor ID to the department table, then you will have an issue, right? Because in each department, we have several advisors working in that department. So you cannot just add them here. And then the same for the student, right? So a student also connected to advisor because each student can have, for example, an advisor. Advisor also can advise several students. So this is also an example of one-to-many here. So the assumption was that each student can have only one advisor. And if that's the case, we can add advisor ID or the primary key of advisor table to the student table. Do we always put the foreign key on the many side in one-to-many relationship? Yes, always, because you cannot put it in the into the other side. That was what I was just explaining. So imagine you add, like for example, for the connection between department and advisor, right? So we added department name, which is the primary key here. We added this to the advisor table. Now, what if you add advisor, for example, ID? Let's say you have also advisor ID here as the primary key. Adding advisor ID to the department, uh, it violates data integrity in department and the relational databases rules, right? Because in relational databases, we said we cannot store multiple values in one cell, and values should be atomic, right? What does that mean? For instance, you cannot, like, if you had another column here, let's say if you had advisor ID here, then in each department, for example, in accounting, how many advisors do we have? Do we have only one advisor that we can just write it here? No, we have several advisors here. And so if I find the, so ideally you should have department ID here. So here you also have another column, department ID, right? So this is department ID, which is your primary key. So this is a better primary key compared to department name. Why? First of all, we may have two departments with the same name, but even if that's not the case, even if we have, for example, we are 100% sure that department names are completely unique, even in that case, still having numerical primary keys better, because it also makes, for example, later make access to the database faster. It's often more efficient than, for example, text features or text fields here. Now, and also, like, department names can change later, right? So for example, you may slightly change the name of a department, and you don't want to change the primary key values. So that's another, that makes inconsistencies, and we don't want to do that. However, with, like, if you have unique identifier like department IDs, student number, things like that, these never changes. So you don't have any issues with that. That's also another reason why, for example, some columns, like, for example, features like email are not good candidates for primary key, because even if, like, you say, okay, in my database all emails are unique, okay, that's just a candidate key, not still a good primary key, because these emails can change later. And so let's say you have department ID here, and here we also have, let's say, advisor ID as your primary key. So this is also advisor ID, which is your primary key. Now we have two options when we want to link these two tables, because in your ER model, what do you have? You have, for example, department table, department entity here, right? So this is department, and this is advisor. So this is also advisor. And so we know that they are connected, right? What is the relationship? One to many. And so in each department, we can have several advisors, right? For example, one or many advisors working in that department. And also each advisor should only work in one department, and they should work in a department. So this is an example of one-to-many relationship. Now, when you convert it to your relational schema and later to your tables in your relational database, you should have a separate table for department, separate table for advisor, as you see here. And how do you represent this link? So in ER modeling, you represent these links using, for example, the relations that we have here, right? And these lines. But in your tables, you have to add foreign key, or it's often through a foreign key, sometimes also through another common field, which may not be necessarily foreign key, but the connection is 99% of the time through a foreign key. Now, where should you add that? For example, foreign key. Should you add department ID to the advisor table, which we did, for example, here? We added department to the advisor table. Or should you add, for example, advisor ID to the department table? Now, if you're adding advisor ID here as the foreign key, so this is advisor ID. So if you're adding this as your foreign key, that is, you're adding foreign key to the one side, not to the many side, because the many side of relationship is advisor, right? But we are adding this to the department table, which is on the one side of the relationship, not on the many side, right? Now, if you add advisor ID here, in each department, for example, in accounting, we have several advisors, right? So you have several advisors here, advisor 1, advisor 2, and so on. So can you store your information like this? No, you cannot. So in relational databases, we cannot store multiple values in a single cell for many reasons. Because, for example, later, if you want to access a specific value inside a field, then you're not able to do that. Although you can do, like, for example, some text search, but that's not efficient. And when we learn about SQL queries, you see that, for example, when you want to access this data, it's much more organized and more efficient if you store each value in a separate fields. That is, you don't have multiple values in one field. So because in each department we have different advisors, and we cannot store like different advisors in just one row, that's why we always add the foreign key to the many side of the relationship, which means department ID, or in this case, department name is your foreign key. So foreign key is basically, so this is not correct, right? So you cannot add this as the foreign key. So foreign key is basically primary key in another table, right? So this, for example, department name, which was the primary key here, or if we had department ID as the primary key, then we had to add department ID as the foreign key, right? So whatever is the primary key here will become the foreign key here. So this is department ID. And is the concept of foreign key clear? Okay, Jade, do you have any questions for this? Did you understand why we added to the many side?
No, I'm good. Thank you.
Okay, great. So this is why we add foreign keys to the many side, because, for example, in this case, each advisor is working only in one department, and so we are good, right? The same thing for advisor and a student. So you have, for example, a student table here, right, or entity here. So a student have an advisor. So there is a relationship between a student and advisor. How do you show that relation? Like this, right? Using this relation, you show the connection between these two entities. So each student have one and only one advisor, and each advisor can have, for example, 0 or more or 1 or more. Let's say, for example, 1 or more students. Now, this is also an example of one-to-many relationship, right? In your exam, you have to also write the name of the relations also in your assignment here, because I'm not really good with this drawing pen. I didn't write names of the relationship, but in practice, you have to write it. For example, each student has, and these relationship names should make sense. For example, advisor work in a department, right? Or each department have several advisors working in that department. Now, this is a one-to-many relationship, and when you convert it to your tables, then you have an advisor table, which you see here. You also have a student table, which you see here. Now, where should we add the foreign key? To the many side, right? Which means to the student table. Why? Because here, each student has only one advisor, right? So you don't have any problem. You can easily add advisor ID or advisor name here. Here we added advisor name because in this example, advisor last name was considered as primary key, which is not the best option. So if it was me, I would have done, for example, like in practice, I think advisors should have employee ID, things like that, right? So we should have some advisor ID here, which is our primary key. Now this primary key here will be added as a foreign key. That is your advisor ID. So if advisor ID is primary key, this will be the foreign key in the student table. So this will be your foreign key. Why? Because foreign key is basically a primary key in another table. This was primary key in the advisor table, so become foreign key here. What is the role of foreign key? To connect tables together. So this is the exact role of foreign key. So we could add these, for example, relations and symbols here to show the connection between these two tables. Now uh, in our database, we can show it with the foreign key. So this is connection between this and this. This is how we link these two tables. Now we added advisor ID to the student table because each student can have only one advisor, and then there is no problem. So advisor 1, advisor 2, and so on. So, but we couldn't add, for example, a student ID, let's say, or student number here. So these three tables do not have the best primary keys in the example in this slide. So please consider something like a student number, employee ID or advisor ID, department ID, things like that for their primary key. And so this is, for example, primary key here. So as Jed asked, maybe someone say why we cannot add a student ID to the advisor table, because then each advisor can advise multiple students, right? So if you add a student ID here, then you have to store multiple values in one cell. For example, for advisor Baker, you have to store several students. And then for advisor Green, you have to store multiple students. So because you cannot store them all in one cell, again, someone may argue that, okay, I'm going to spread them in different rows. So for example, advisor Baker, for example, student Mona, advisor Baker, student, for example, I don't know, Hannah, and so on. That is also not correct, because if you want to do that, then you're repeating advisor ID. In the advisor table, an advisor ID is the primary key, which is not possible again. So we have no other way than adding your foreign key to the many side, which is adding advisor ID to the student table, which doesn't have any issue. Now I have a question. Can foreign key be repeated, or should they be unique? Can foreign keys be repeated here? Yes, they can be repeated, right? There is no problem because, for example, let's say Andrew's advisor is, I don't know, Baker, right? And then again, Fisher has also the same advisor, and so on. So there is no problem. This is not our primary key. This is not a unique identifier here. So advisor last name, advisor ID here are not unique identifier in the student table. It's just a foreign key. And foreign key can be repeated. Now, I don't know if all instructors are so super slow with the drawing, or is it only me? So, very important topic, functional dependencies. Let's just read this definition, which looks very difficult, but then when I'm going to explain it with examples, you see that it makes total sense, and it's not that difficult. So given a relation R, and by relation we mean relational table. So given a relation R, attribute Y of R is functionally dependent on attribute X of R. So it is expressing dependency between two attributes of relational table R, for example, attribute X and Y. If and only if, whenever two tuples of R agree on their X value, they must necessarily agree on their Y value. And then we show this dependency like R dot X, it can uniquely identify R dot Y, or we can read this as R dot Y or attribute Y is functionally dependent on attribute X. So there are two ways to read this, and please be careful of the order. So here, this, what you see here, this means that Y is functionally dependent on X, or attribute Y is dependent on attribute X. For example, let's say instructor office is functionally dependent on instructor name. Why? Because instructor name can uniquely identify its instructor office. This means if I tell you, for example, instructor name, for example, Mona, you can uniquely identify my office, right? So Mona instructor office is, for example, CB140. And so this is the meaning of what you see here. So we say attribute Y, for example, instructor office, is functionally dependent on attribute X, for example, instructor name. If and only if, when two tuples agree on their X value, they must agree on their Y value. That is, for example, if I tell you what instructor name is, you should be able to uniquely identify instructor office. Now, when the value of one or more columns in each row of a table or relation uniquely identify the value of another column in the same row of that table. That is what I mentioned. Now, let's see it with some examples. So we have three types of functional dependencies. We have full key dependency, we have partial dependency, and we have transitive dependency. And I'm going to explain this today. In general, full key dependency means that a column is functionally dependent on a primary key, and no other component of the primary key partially determine the same column. So, for instance, let's say here, you have a relation, a student ID, a student name, course ID, course title, and grade. So if you have a table like this, my first question, is table normalized? Is this table normalized? No. Why is this not normalized? Because we are storing separate information about separate entities in one table. There are several anomalies here. For example, if you delete a student Dave, right, then you may also lose other information, which is actually not the case here. If you lose, for example, because we have two of them, but it could be in another example. Or for example, um, there are several dependencies here that I'm going to explain. So what is the primary key? In order to identify dependencies, the first step is to find out what is your primary key. So what is your primary key in this table? Primary key should uniquely identify each row. Does a student ID in this table uniquely identify each row? Composite keys, thank you. We have composite primary key, Jade, right? That is correct. So a student ID in this table cannot serve as a primary key. Course ID the same, grade the same. Why? Because they can be repeated. For example, here, as you see, we have a student ID repeated, right? Course ID also repeated, and the same for the grade. And even if they were not repeated in this example, in this specific example, they couldn't, like, still they couldn't be a good primary key, because in future we may have, for example, um, we may see, for example, same student name. Why? Because we are storing course and student information together. So for instance, in the database course, right, we don't have only one student. In database we have several students, and that's why you're seeing repeated student ID here. So in practice, in database you may see, for example, 140 students, right? So you will see database is repeated. The same thing, you will see a student, you know that each student can enroll in several courses. For example, Susan is enrolling in both database and data mining, right? So you see that the student name is repeated. So we will see both course title, course ID, and student information. They are all repeated because there is a many-to-many relationship here. And we are storing all this information with all these dependencies in one table. So none of these columns can uniquely identify each row, and none of them are unique. So what is the next, for example, option for primary key? So if you don't have a unique column that can uniquely identify each row, you can think of composite primary key. And composite primary key is just a primary key that is composed of two or more columns. Now in this case, a student ID and course ID together can uniquely identify each row if you consider that each student is enrolled in each course once. Now, if you had, for example, something like, if you had, for example, term here or semester, right? For example, let's say this student is taking database in fall, and then same student, let's say same student, Susan. So I just write S, but I mean actually this student, right? So if, for example, Susan is taking the same course, right? If it's taking the same course, for example, database also in winter, right? That could be possible. So if your assumption is that each student can take each course multiple times, can we say a student ID and course ID can uniquely identify each row, or are they a composite primary key? No, because then this student and this course are repeated. So student ID, this, like Susan Water, and database are repeated. So this is not unique. But in this case, in this example where we don't have this information, and let's say our assumption is that each student can take each course only once. So if this is our assumption, then a student ID and course ID together can form your composite primary key. So this is our primary key. Now, whenever you have composite primary key, you have a chance of, like, not necessarily, but there is a chance of having a partial dependency. And what is partial dependency? Partial dependency means there is a feature or column in your table that depends only on one part of your primary key. So if your primary key is, like, for example, a student ID, so if this together with course ID, so if this is your primary key, so let's say student ID and course ID, this is your primary key. Now, do we have a column here that depends on only one part of your primary key? That means that depends only on student ID or only on course ID. So Arsha, in that case, the primary key would be student ID, course ID, and term. So 3 columns. Name depends only on a student ID. Thank you. So a student name, right? A student name only depends on a student ID. Or we can say student ID can uniquely identify a student name. So when we say X or R.X, right? R.X can uniquely identify R.Y, right? So this is our relation or this table. Now, X can uniquely identify Y. What is that here? For example, a student ID can uniquely identify a student name, right? Which means a student name depends on a student ID. For instance, if I give you a student ID, for example, 401325, can you uniquely identify a student name? In other words, giving you this student ID, can you find a unique name for this, or is this associated with several student names? Unique, right? So each student ID can uniquely identify each student because each student has only one student number, right? So each student number or each student ID belongs to a specific and unique student. So a student ID can uniquely identify a student name, or a student name depends on a student ID. Now this is one dependency here, and we call it partial dependency. Why we call it partial dependency? Let me also write the type of dependency. So we have full key that I'm going to explain now. We have partial, which means, for example, you have a column, like for example a student name, that only depends on part of your primary key. For example, if you have a composite primary key like a student ID and course ID, a student name only depends on a student ID and doesn't depend on course ID. Why? For example, can I write course ID? Course ID identify is here, instead of course title I write the student name. Can course ID uniquely identify student name? No, it cannot. Because if I tell you, for example, course, for example, ECS 3421, you cannot uniquely identify students, right? In this course, there are many students. So if I tell you 3421, you cannot tell me a unique student name. So that is not dependent on course ID, and it only depends on part of primary key. This is an example of a partial dependency. Can you give me another example of partial dependency here? Another example of partial dependency. Course ID, course name, thank you. Yeah, course ID, course name. Because if I tell you course ID, for example, 3421, you can give me one unique course title, which is the database. So 3421 is only database. It is not data mining, it is not AI, it is not mathematics, and so on. So it can give you a unique course name. So course ID can uniquely identify course title, or we can say course title depends on course ID. Now, this is also an example of partial dependency. So the first two dependencies are partial dependencies. Now, if I tell you, for example, a student ID, course ID. So do we have this dependency? Can a student ID uniquely identify course ID? It is not full. I'm going to explain full later. Full key dependency means you have a feature or you have a column in your table that depends on all part of your primary key. That depends on the whole primary key, not only part of that. Yeah, so in general, if you have a single primary key, let's say you have a student table, right? If you have a student table, what would be the primary key? A student ID or a student number, right? Now, in a table with single primary key, all columns, like for example, a student number, a student name, and so on, a student email. So all these features depend on the primary key, because primary key always can uniquely identify each row. So that is always a full key dependency. So in a student table, if I tell you student ID, student name, that is an example of full key dependency, because in that case, in the student table, a student ID is your primary key, and a student name depends on the full primary key, right? Not only part of that, because we don't even have a part. There is only one single primary key. In a table with composite primary key here, can you give me an example of a full key dependency? Great, exactly. Grade depends on both the student ID and course ID. So if I write a student ID and course ID can uniquely identify grade, or grade depends on a student ID and course ID, this is an example of a full key dependency. Why this is full key? Because a student ID and course ID, these together, they form your primary key, and grade depends on both of them. None of these columns alone can uniquely identify grade. Why? Because if I tell you, for example, a student ID, right? Can I say student ID can uniquely identify grade? No, because for example, two students may have the same grade, right? And if I tell you course ID, for example, 3421, can I uniquely identify grade? So if I tell you, for example, 3421, can I say it's always A plus? No. We have several students in this course. They may get different grades. And so as you see, we have A plus and B. So giving, for example, course ID. So if I give you course ID, as you see in this example in this table, you cannot uniquely identify grade. So let's say this is grade. This is not the case, right? But now if I tell you, for example, Dave Hamilton 3421, then can you uniquely identify grade? Yes, because each student, we assume that each student take each course once, and so they have only one grade in that course, right? And assuming that this is final grade. So only one grade and a unique grade, so you can uniquely identify grade in that case, or grade depends on both a student ID and course ID. So this is a full key, an example of a full key dependency. So whenever you have a composite primary key, if there is a column that depends on all parts of your composite primary key, like for example grade here, or if you have a single primary key, let's say you have a student table, right? So if this is a student table with a student ID, which is your primary key in the student table, right? So this is your primary key. Then all other columns in the student table, like for example, sorry, I don't write the names because I'm not very comfortable with this like drawing pen, but if this is, for example, a student first name, last name, email, phone number, and so on, a student ID can uniquely identify each of them. That's why that's the definition of the primary key, right? Primary key is a unique identifier of each table, or we can say primary key, for example, can uniquely identify each rows. So all these features, all of them, uh, are dependent on a student ID, or we can say that the student ID can uniquely identify student name, email, phone number, and so on. So if I tell you, for example, this is student ID, you can tell me what is its name, what is its phone number, what is its, for example, email, and so on. But in this table, this is like, for example, an enrollment table. In this table, we have composite primary key, and then we have to check if for each feature, we have to check if they depend on part of primary key. If that's the case, like a student name on a student ID, that's partial. Similarly, course title depends on course ID's partial dependency. But for example, grade depends on both course ID and student ID, which means grade depends on all part of our primary key. So that is a full key dependency. Now, back to the example, a student ID, course ID. Do we have this dependency? Or for example, can a student ID uniquely identify course ID? No, there is no such dependency. Course title, a student name. So if I give you course title, for example, database, can you uniquely identify student name? Is it associated with only one student name? No, because in each course we have several students, so that's not the case. This is also not, there is no dependency. So no dependency, no dependency here. A student ID, grade. If I tell you student ID, can you uniquely identify its grade? No, because on what course? A student ID, for example, let's say this student got A plus on database, A on data mining, and maybe get, for example, C on another course, fail on another course, and so on. So this is also not a dependency. How about course ID, grade? Similarly, no, right? Because, for example, if I tell you 3421, you cannot uniquely identify the grade. 3421 is associated with A plus, right? And also B, depending on which student took this course, right? For example, Susan got, for example, A plus on this course, Dave got B, and other students different grades. So it cannot uniquely identify grade. So do you have any questions here?
Hello.
Yeah.
I have a question about normalization. So this table looks like an associative entity, right? An associative entity table.
Yeah, this is an enrollment, which is
Yeah.
actually associative entity.
So it's okay for associative entities not to be normalized because we assume that they're broken down into different tables for like separate entities, right?
Yeah, yeah.
Okay, thank you.
But still, like, no, actually it depends. So for example, here in this specific case, we can still normalize this table, and we don't care about full key dependencies, but we care about partial. We want to get rid of partial dependencies and transitive dependencies. Why? Because full key dependency exists in all tables, even like a student table, course table, because all tables have a unique, they have a primary key, right, or unique identifier, and all features depends on that. Or for example, primary key can uniquely identify each of them. So in that case, we don't care. So if you have a table with only full key dependency, then you can leave it as is. But enrollment table here, we can still have enrollment table, although it's associative entity converted to a table, but we can still normalize this. Do we need to have a student name and course title in this table?
No, so we would
No.
only keep student ID, course ID, and grade. That would be
Exactly. So
FBL,
we
right?
can, yeah, we still have associative entity converted to this intermediary table, but with only a student ID, course ID, and grade. So we do not need a student name here. We do not need course title here. Why? Because we have a separate table for a student. We have a separate table for course, right? And here we have partial dependency between a student ID and between a student ID and a student name, and also between course ID and course title, right? And that's why it's very important to identify dependencies, to correctly identify dependencies, because it helps you with normalization. If I tell you to normalize this table first, for example, in the exam, I may give you a table like this, and first I may ask you what normal form this table is. So you have to identify the normal form, which I'm going to explain today, and that is identified based on types of functional dependency. For example, if you have a partial dependency, it means that the table is not in 2NF. If you have transitive dependency, it means that table is not in 3NF. So 3NF means no transitive dependency, no partial dependency. 2NF means, for example, no partial dependency, and so on. So you don't have to know that right now. I'm going to explain it later. But first step is to identify the dependencies. Now, full key dependency means a column depending on all part of your primary key, and we don't care about that. It's okay because by definition, primary key should uniquely identify each rows, so we don't have any issues there. But if there are partial dependencies or transitive dependencies that I'm going to explain in a few minutes, then we have to get rid of them. Now, how does it help? How does it help with the normalization? Easy. So first you find the dependencies. For example, you say student name depends on a student ID. So we get rid of this dependency, which is a student name. Also, course title depends on course ID. So you get rid of course title and put them in a separate table, right? So a student ID, student name will be another table. So this will be another table. This is for a student. So a student ID and a student name. And of course, you may have more features. It doesn't matter. So the main point is that you break this dependency and put it in a separate table. And also you have another table, course ID and course title, right? So course ID and course title, because there was a dependency here, which you don't want. Now here there is no issue in terms of dependency between a student name and ID, right? Because this is a student table and we expect that a student ID uniquely identify each row because a student ID is your primary key and this is your whole primary key. This is a single primary key. So this dependency is a full key. We don't care about full key in normalization. And here the same, course ID is your single primary key. This is just a single column, and there is no partial dependency here. We don't care about these two. This is a full key dependency. But in this specific table, we have to get rid of these dependencies, right? And this is because of the relationship between student and course. So we cannot keep this like this. Now, do you have any questions or can I move on to other types of dependencies like transitive dependency? So let's go to the next slide. Now, what are the normal forms? So we say relation is, by relation I mean relational table, right? Is said to be in a particular normal form if it satisfies certain specified set of constraints. And those set of constraints are dependencies that I'm going to explain. So first normal form means we have to remove repeating groups. So when we say that this is the lowest part of lowest form of normalization. So it just means that you don't have any repeating groups and each cell should have one value. That is, you have to store atomic values in your tables. So after normalizing, we would only keep a student ID, course ID in the table. We keep a student ID. Sorry, I'm answering Leah's question. So in this example, after normalization, we can keep a student ID, course ID, and grade. We can keep grade because grade depends on both part of primary key, that is a student ID and course ID, which is a full key dependency, and there is no problem. Is that clear, Leah? Okay. Now, so 1NF or first normal form means that each cell should have only one value. Like, for example, what I mentioned about, for instance, here, right? If you have, sorry, here. Recall when I was talking about adding foreign keys to the menu side, I said that you cannot add, for example, advisor ID to the department table. And this is because, for example, in each department, we have several advisors and we cannot store multiple values in one cell, right? So we are not allowed to store multiple values in one cell. And that's about atomicity of relational tables. So each cell should hold only one value. And then 2NF is about removing partial dependencies. So we learned about partial dependencies. We know that, for example, partial dependency happens when you have a column that depends only on one part of your primary key. So if you have partial dependency, your table is not in 2NF. And you have to first get rid of those partial dependencies, and then make your table 2NF. So 2NF means first, the table is already in 1NF and also there is no partial dependency. Then 3NF means the table is already in 1NF and 2NF, that is no repeating groups, each cell holding one value, also no partial dependency. But on top of that, there shouldn't be also transitive dependencies. I'm going to explain transitive dependencies just in a few seconds. And then we also have other forms of normalization, like for example BCNF, which is a stronger version of 3NF, ensuring that, for example, only keys can determine other columns. We have 4NF, removing all multi-valued dependencies. For example, if you have a student hobby language in the table, then each student can have several hobbies and can speak several languages. So how can you fix this? You can split it into two tables, one storing a student hobby, the other table storing a student language, and also 5NF, that is breaking down complex joint dependencies, which are out of the scope of this class. So for this course, for the scope of this course, you only need to learn 1NF, 2NF, and 3NF. So a table or relation is in 1NF or first normal form if each row or record is unique and no column in any row contains multiple values, so no repeated groups. You cannot store two different things in one column. If I want to tell it very clearly, you cannot store two different things in one column. For example, you cannot store customer address and email address both in one address column. So you cannot have, for example, let's say you have a customer table with customer ID, customer name, and so on, and then you have a column like address, and then putting, for example, both customer address and email address there. You cannot do that. You cannot store multiple values in one cell. And also, you cannot have multi-valued facts in one cell. For example, two different email address in one email address column. Let's say in your customer table, customers may have more than one email, right? So for example, I may have Gmail, I may have my York email address. So if I'm a customer, let's say in the customer table, and we have a column for email, what do? Can you store, like, for example, customer ID, customer name Mona, and then store multiple, let me draw that. You cannot store multiple emails in one email address. There are several ways to address that. We can store them in different features or a separate table, but you cannot store them in one cell. So 1NF, just in summary, means atomic values. Atomic values means that you cannot store different things in one column or multiple values in one cell. Now here's an example. So looking at this table on the top, so this table here, is this table normalized? No, this is not normalized. Can we say this table is in first normal form? First normal form means each cell should store only one value. We cannot store multiple values in one cell, or they should be atomic. No, this is not in first normal form. So this table is not in first normal form because, for example, you see, for a student ID or student name Williams, for this student, we are storing multiple courses, database management, system analysis, these two different courses with two different instructors, with different locations and different grades, right? So you cannot store multiple values in each cell. So why is we cannot do this? Why is this not efficient? What is the problem with this? Anyone? Yeah, I know what, but why we cannot store multiple values in one cell? Data integrity. And later, for example, when you want to query your tables, when you learn about SQL queries, you see that, for example, you cannot, because you're accessing by primary keys the tables, and then here, for example, for one student, we have different courses, different instructors. So if you want to access each of these, then that is not possible unless you do like some text search, which is possible in SQL, but then that's very complicated. And So that's why in relational databases we say we do not store multiple values in one cell. So here we have multi-valued facts in each cell for course ID, course title, etc. And we need to separate them with adding more rows. For example, storing each information in one row. So that's one way. And so first normal form or 1NF is sometimes described as removing the repeating groups. By repeating groups, I don't mean that they are the same, but I mean like, for example, for this student, then you have this and this, right? Two groups of information. And we have to get rid of that. So each cell should contain only a single value, not list of values. And so this is not in 1NF. Now, what does I want you also to emphasize that we don't have to confuse it. For example, first normal form, it doesn't refer to duplicate values across rows. For example, IS IS 350 appearing for both Williams and Baker, right? So that's no problem. So this IS 350 appearing here and here, that is no issue. But the issue is that we store like two courses here or three courses here, two instructors here, and so on. That is the problem. And so repetition of the same value across rows is okay in relational model. For example, many students can take the same course. That's not violating on 1NF, but repeating groups or values that are not atomic, that violate 1NF. So this table, the upper table, is not 1NF. Now, if we want to normalize it to be in 1NF, we should get rid of these multiple values in one cell, right? So for example, we can separate it into two tables. One table is storing like this information. So up to here, we don't have any issue. So student number, student name, campus address, major. So there is no issue up to here. But here, like here, how can we get rid of like these repetitions? We can store each of them in separate rows, right? For example, now we have for example, this course. Of course, you also have to include a student ID, right? So that you know, for example, each student took which course. So for example, a student ID this, and then course ID, then the first course title, then you go to the second row, same student taking a different course, right, with different instructor, and then the next row again, so you do like the first student, this is going to the first row, second row, and third row. So basically what you're doing is like this. So right, so this is what you're doing. So now you have like these 1 2 3 4 5, right? So you have like these 5 courses, and of course you have to also mention the student ID so that you know each student took which courses. And what is the primary key here? What is the primary key in the table on the bottom right? This table, SID and course ID, right? Student ID and course ID. Correct. Yeah, that is correct. So student ID and course ID together form composite primary key here. And is this table in second normal form? This table and the bottom right, is it in second normal form? No. Why? It still has partial dependency. Exactly. So this has a still partial dependency. So as you see, course title depends on course ID, right? Also, for example, instructor, can I say there is a dependency, partial dependency between instructor name and location? For example, if I give you instructor name, can you uniquely identify instructor location? Yes. So there is also a partial dependency between this and this. But is this partial dependency? We can say there is a dependency here between instructor ID and so let me choose another different color. So we can say that instructor location depends on instructor ID or instructor name, right? Or instructor name can uniquely identify instructor location. So is this partial dependency? What is partial dependency? Partial dependency means there is a column, like for example instructor location, that depends on only one or like some part of primary key. What is primary key here? Primary key is a student ID, course ID, right? So this is your primary key. This is a composite primary key, right? So you have a composite primary key. Now, the relation, like the dependency between course ID and course title, of course, is partial dependency because as you see, course title depends only on course ID and not a student ID, right? So because course title depends on only one part of, or like just part of your primary key, right? Part of your composite primary key, this is partial dependency. But the dependency between instructor name and location, this is not partial. This is transitive dependency. And so transitive dependency is a dependency between two non-key columns. And by non-key, I mean non-primary key. The column can still be foreign key and that's fine, but cannot be primary key. Now, for example, is instructor name here part of your primary key? No, this is not part of primary key. So this is not a partial dependency. This is transitive dependency. So far, we learned about three types of dependencies, right? First is full key dependency. That means you have a column or feature that are dependent on all part of your primary keys. Now, if we have a table with single, for example, primary key, then the dependency between each column with the primary key is full key, right? Because primary key can uniquely identify each rows. In a table with composite primary key, like for example this one, can I say, is this correct? If we have a composite primary key, we will have a partial dependency. Is this correct? If we have a table with composite primary key. So I repeat my question. If we have a table with composite primary key, can I say we will have a partial dependency? Not necessarily, right? We can have only student ID, course ID, and grade. So we still, if we have a table with, for example, a student ID, course ID, and grade, so this is our enrollment table, let's say, a student ID, course ID, and grade. So let's see what normal form is this table. And then let's say we store only single value in each cell, for example, a student ID 1, course ID, for example, 3421, and then grade, for example, is A. And then the next row, like similar, and so on. So we only store single values in each cell. If we have atomic values, that is storing only single values in each cell, it means that the table is in 1NF, right? So this table is already in first normal form. Now, what is the primary key? In order to identify partial dependency, you have to identify your primary key. If in a table with, for example, composite primary key like this, we have a column that depends only on part of your primary key, then that's partial dependency. Like for example here, when course title only depends on course ID and doesn't depend on a student ID, right? Because if I give you a student ID, then you can tell me different course titles. Each student can take multiple courses. But if I tell you course ID, then you can uniquely identify each title. 3421 is the database course. Or for example, this course is database management, and so on. Now, what about this table? This table still has composite primary key, but we do not have any partial dependency. The dependency between grade, right? Grade depends on both a student ID and course ID. So this dependency is full key dependency, right? And it doesn't violate the second normal form or any normal form. So this is okay. And so this table is also in 2NF. Is this table also in 3NF or third normal form? What should we do for 3NF? We should check for transitive dependencies. Do we have any transitive dependencies here? No. Transitive dependencies means there is a column that is non-key, depends on another non-key column or non-primary key column, right? For example, instructor location depends on instructor name. Now, this instructor name, or if we had instructor ID, then we had dependency between instructor name and instructor ID. Instructor ID in this table is a foreign key, right? Because instructor ID is primary key in the instructor table. So if, let's say, if we had instructor ID in this table, so let's say you had instructor ID. So if you had instructor ID is the foreign key, right? So this is the foreign key. And then what would be the dependency? Then we could say, for example, instructor ID, right, can uniquely identify instructor name. It can also uniquely identify instructor location, or we can say instructor name and instructor location depends on instructor ID. And this dependency is a transitive dependency because this is a dependency between non-key columns, and by non-key I mean non-primary key columns. That is, your instructor ID is not primary key here. So this is a transitive dependency. Do we have any transitive dependency here in my example? No, we don't have any transitive dependency. So the table is also in 3NF. It is in 3NF because, not only because there is no transitive dependency, but because there is also no partial. So the table, for a table to be in 3NF, it should already be in 1NF and 2NF. For a table to be in 2NF, it should already be in 1NF, right? Now, if a table has atomic values, this is just a summary. So if you have atomic values, then it is 1NF. If it is 1NF, so if it is 1NF, and also you don't have, 1NF, and no partial dependency, so let's say no partial dependency, then this is 2NF, or second normal form. Now, if a table is already in 2NF, which means it's also in 1NF, right? Plus no transitive dependency, and there is also no transitive dependency, then the table is in 3NF, or third normal form. Now, one last question, and then you're free to go. If we have a single primary key, if we have a table with single primary key, can we have partial dependency? No, we cannot. If we have a single primary key, how can we find a feature that depends only on part of our primary key? The primary key is only one part, right? So be careful. When I give you a table to normalize it, first look at the table and see if there is repeating groups, if you store multiple values in one cell. If that's the case, the table is not even in 1NF. And if the table is not in first normal form, it means that it is not 2NF, not 3NF. Now, most of the cases I give you a table that is already in 1NF because my goal is to understand if you learned, for example, the dependencies. So let's say if a table is already in 1NF, I give you, for example, a table, and then if the values are atomic and no repeating groups, okay, this is 1NF, fine. Then you have to check your primary key. If there is a single primary key, don't wait. Like immediately you can identify it as 2NF. So if single primary key, it's 2NF, right? There is no chance of having partial dependency. And if we have no partial dependency, means that it is in 2NF. Now, if you have a composite primary key, can you immediately say that it is like partial, it has partial dependencies? No, it depends. So if it's single primary key, you can immediately say the table is in 2NF. Or maybe even in 3NF, but at least you can identify it up to 2NF. If it is a composite primary key, then the table might or may not have a partial dependency, but you have to check. If you find a column like, for example, course title here, it depends only on course ID, or if you had a student name, depends only on a student ID, in that case, the table is not in 2NF because of partial dependency. And then when the table is already in 2NF, you can check for 3NF. If it is not, then you say, okay, this table is not in 2NF, the highest formal norm is 1NF. But if not, if you already found, for example, partial dependencies, you also need to check for transitive dependencies, because table might be still in 2NF or 3NF, right? So up to here, we found that this table is 2NF. For 3NF, you also check for transitive dependencies. For example, instructor location, instructor name, or for example, instructor ID can uniquely identify instructor name and location. So these are examples of transitive dependencies. And if you have these, it means that your table is not in 3NF. So that's it for today. Do you have any question? Why does the student info need to be separated into a student table for 1NF? So in general, a student information should be in a separate table. It is not only because to make it into a 1NF. So 1NF is not about that. It's not about dependencies. 1NF is only about having no repeated groups or making sure that all values are atomic. So the fact that we wanted to have, for example, a student information like in a separate table, right? So there are several reasons. First of all, we wanted like this information in these different in these in this different table and different rows, right? Because we wanted to avoid repeating groups, and also because we wanted to have atomic values. So this is why we put this information here. Now you tell me, okay, what if we had also a student name, campus address, and major here, right? Is that your question? So instead of having two tables, having only one table, and storing a student name, address, major also in that table. So if that's your question, that is not efficient. So as we explained before, we try to separate dependencies, right? We want to get rid of the dependencies. And so if you want to normalize this table, this is not even the end. So you have to even like store another, like create another table for course, not only a student, but also course ID, course title. So this is the whole, like this is not complete. If you want to have the like complete normalization, you have to have a student table, course table, and then another table for instructor. Or in other words, you want to get rid of all the dependencies. So for example, in order to get rid of dependencies between a student name and a student ID, you put them in a separate table. In order to get rid of dependencies between course title and course ID, you put them in a separate table. In order to get rid of like transitive dependencies between like instructors, you put them in another table. How does it resolve these dependencies? Because when you put, for example, course information in a separate table, then dependency between course title and course ID is not an issue anymore, right? Because here course ID alone is your primary key. So this is a single primary key, and this dependency is full key dependency. Full key dependency doesn't violate anything, right? And that is fine. So in this case, you don't have any problem. Similarly here. So here you have a student ID as your primary key, and then a student ID can uniquely identify student name. So this dependency is full key dependency, and we don't have any partial dependency. We don't have any transitive dependencies. And similar case with the instructor table. But if you want to keep it like this way, what would be your primary key here? A student ID, course ID, right? And then a student ID depends on, sorry, a student name depends on a student ID, or a student ID uniquely identify this. So this is one partial dependency. This is another partial dependency, right? And we also have a transitive dependency here. So this is transitive. And these two are partial. So this is partial dependency, this is partial dependency. So we want to get rid of them. So we first separate this, and then for this part, before we separate course into a separate table, right? Before we do that, similar to sorry, what we did for a student, we have to first make it 1NF, right? Because this is not, this part is okay. So if you can separate this, but for this part, you have to first make it 1NF. After 1NF, you can then get rid of the partial dependencies to make it 2NF and 3NF. Is that clear? Which one? You said would that at least be in 1NF? This one, the one on the bottom right. So the table on the bottom right is in 1NF now. So this table is in first normal form. And this table is in 3NF. So Andrew, did I answer your question? Okay, so this one is 1NF. This table, this like the table, the large table on the top is not even in 1NF. So this is not normalized at all. This is not even in 1NF. Do you have more questions? So if you don't have any questions, we can end the class. Yeah, I'll stay here. For those of you who have like personal questions, you can leave the class. So have a great day. Okay, about the midterm. Sorry, about the midterm. Uh, yeah, I can record that, but I will also send an announcement including more complete like information about your midterm. Like for example, how many questions. So when we get closer to the midterm date, I can give you even more detailed information, like how many questions we have, how many, for example, multiple choice, how many problem solving. But in general, like midterms are like this. We cover everything before midterm, that is before SQL, which includes introduction, ER modeling, data modeling, relational databases, and normalization. So all the topics that we cover before the midterm, except SQL. So SQL is going to be for after midterm. And then in terms of the structure, you will have a mix of multiple choice true false questions with some problem solving. For the problem solving, I may give you, for example, a case for ER modeling. So it will be something much simpler than your assignment one. So if you have already done assignment one and also the ER part of your final project, you should be really good with the ER in your midterm. I may also give you normalization question where I may give you a table that is not normalized, ask you to identify the normal form and normalize it step by step up to a certain normalization, or asking about functional dependencies and so on. So it will be mixed. And also in terms of weight, should be half and half or even more weight towards problem solving questions. How often we do Kahoot? Like starting now that we finished normalization, we will have more frequent Kahoots, especially for the SQL part, data warehouse, and so on. For this part, my first Kahoot is covering questions, include questions that covers both ER modeling and also normalization. So I had to finish this topic first before doing the Kahoot. So probably next session we should have a Kahoot. So is there any more questions? Have a great day. Have a great day.